so these are not Hermitian operators, but this .hc will recover us back Hermiticity of the Hamiltonian. So these sigma operators now, which were originally for sigma z's, they have in the diagonal complex roots of unity. So these are in some sense read down the complex clock as it winds, and the tau operators wind the clock. Okay, so these are again the generalizations of sigma x, if you would like. Okay, and then in general, these clock models have an integer quantity to them, so which tells you how many roots of unity you take into account. And in this particular case, we are focusing here on n equals 3. So this is the n equal 3 clock model. But you could go to n equal 4 and so on and so on. Okay, so you know that if you look at the transverse field Ising model, and then you do a Jordan-Wigner transformation, you can arrive to the Kitaev model, or if you do a bit slightly more different Jordan-Wigner transformation, you immediately can arrive to the Kitaev model expressed in the Majorana basis. Okay, so where there is a mapping between these sigma and tau operators to Majoranas in the transverse field Ising model. And if you follow the same recipe, you arrive to a very similar structure of these operators, with the one key difference that instead of what you would have in the case of Majorana fermions, which would be the n equals 2, these alpha operators have a slightly more weird commutation relation. So in general, there is a complex phase arising in the commutation relation. Okay. However, this model still possesses some of the key features of the Kitaev model. Namely, if we neglect, so this Hamiltonian now in these alpha operators have now sort of inter-site and intra-site type of bondings. So each site will have two alpha operators, the odd indexed and the even indexed operators, and then we are going to have again these dimerization features present in this model. So again, if we concentrate on the fully dimerized limit, where we neglect the inter-site intra-site hopping, then we recover a similar structure what you have in the Kitaev model for the Majoranas. With the one key difference that now in this case the edge has two alpha operators instead of two Majorana operators, and in this case these two alpha operators encode a more highly degenerate ground state than in the case of Majoranas. So Majoranas encode a doubly degenerate ground state. If you start from from a clock model with a characteristic index of n, then in general, in this clock chain, you will have an n-fold degenerate ground state, which is somehow separated into the two edges of the system. Okay, so this is a neat trick, and then people started to think about why is this good for anything. Can we make use of these systems in some real setting? Are they better than Majoranas in any way? So I am now just quickly going to go through a couple of statements from the literature, and if you really would like to go for the detail, I suggest to you to go through this paper by Hatter and Daniel Loss, who would really give you a really decent review of these points. So Majorana modes, as you know, can be potentially realized in systems where interactions do not play a very important role. So, which means that you can treat the theoretical description of these systems usually in the mean field tools. So, of course, you have to have in most realizations some kind of superconductivity. So you have to treat superconductivity to a certain degree, but if you use just the Bogolyubov-Dejean picture, then it is going to be giving you Majoranas, and it's going to be enough. So Majoranas are really nice because they can realize these highly degenerate ground states, which could in principle be used to store quantum information robustly, because they are not sensitive to local perturbations. However, they are not very good to perform operations, quantum operations. So usually people, when they do Majorana type of architectures, at some point you have to leave the topological realm in order to perform universal quantum computation. Okay, so you need there are certain gates what you cannot do with Majorana fermions. There are, for example, no entangling gates in Majorana settings, strictly speaking, in the topologically protected sense, which means that only with braiding you cannot perform universal gate sets. Parafermions, on the other hand, usually require strong interactions. Okay, so you have to go beyond mean field. Basically, this is the important point. So this means that it is a bit more involved to simulate or treat or discuss them theoretically. However, they can realize a more extended set of topologically protected gates. So from the point of view of quantum computing, they promise something which goes beyond Majorana fermions. In particular, with even parafermions, you can already realize entangling gates just with braiding. And now I'm not going to go into very much detail in the last point, because so the key point is that if you would realize odd parafermions, then that would lead a route towards universality, because with odd parafermions you can define Fibonacci anions, and they indeed could be used to encode topologically protected ground state with a universal gate set. Okay. So now I'm going to focus on our in our system on an even parafermion realization, namely Z4. And so there are a couple of signatures what I'm going to look for. Okay. So I would like to have to demonstrate robustness of my my zero modes. I would need to have zero modes which have more degeneracy than Majoranas. These need to be somehow localized excitations. Okay, and they have to go beyond Majoranas in the sense that that the Josephson spectrum is not Z4, but not 4 pi periodic, but 8 pi periodic. Okay, and this is a big distinction between Majoranas. So in certain systems you can encode a 4-fold degenerate ground state, but they are going to be given by a combination of time universally protected Majoranas, and we have to make a distinction between these and parafermions. Good. So what did people do so far? So one simple realization is that if you look at n equals 4 parafermions, then one can realize that then we have to operate in a 4-dimensional local Hilbert space. So there is a natural connection between electrons, so spinful fermions. And then indeed, so there was a paper by Tobias Mauro Sassetti and their co-workers who basically just fermionized the parafermion chain. Okay, and the Hamiltonian in this language looks like this. So it's the dream of all experimentalists. So it has some sort of superconductivity, which is like a mixture of S wave and P wave. Then you have hopping, which depends on occupation. Then you have superconductivity, which depends on occupation. And then you also have three-body interactions. So it's the dream of an experimentalist. No. So it's a very non-trivial to realize this system, and we have to give credit to the authors because they managed to boil down. They managed to connect this complicated Hamiltonian to a Hamiltonian which only requires two-body interactions, but these two-body interactions still remain something which is an occupation-dependent hopping and an occupation-dependent superconductivity. Okay, so just starting from the parafermionic chain, it became it is not necessarily straightforward to realize these systems. So there were some other theoretical efforts a bit more rooted in realistic systems. So starting from setups which use quantum wires in conjunction with superconductivity and strong interactions. And here in these systems, usually the setup was a requirement for superconductivity and strong interactions. Okay. And there was also a really nice review by Alicia and Friendly, where you can also see the other type of realization of these parafermion zero modes required already sort of fractionalized edge modes of a fractional quantum Hall effect in conjunction with superconductivity. Okay, so these are really nice proposals. There was also a proposal which I'm going to focusing on in the remainder of my talk by Zhang and Kane and Orth and his co-workers, which use the edge states of two-dimensional topological insulators with S-wave superconductivity and some time reversal invariant two-electron interactions. Okay, so these are really nice proposals, but the theoretical methods what they have used was bosonization, which means that it is not necessarily transparent what type of interactions you have to consider in these systems, and it is also not necessarily so once you can calculate these things in bosonization, there are certain aspects of these models which neglect, for example, high energy excitations in these systems. So our motivation was to look for this system in a lattice realization, okay, and treat interactions explicitly. Okay, so this two-dimensional topological insulator edge is a system which is something like 1D. So we thought that okay, DMRG is a tool for one-dimensional interactions. So the first theoretical hurdle was to address this issue that we somehow have to treat a two-dimensional system or the edge of a two-dimensional system as faithfully as possible, because we have a really nice tool which is a one-dimensional like system for interactions, which gives us access to a two-dimensional to physics of the two-dimensional system. Okay, of course it is the physics of the edge of the two-dimensional system. Okay, so I hope most of the audience might remember this film. It's Apollo 13. I think it was contributed highly to me becoming a physicist. So I honor this film here now. So now let's talk about the model what we came up with. So it's a model which has three parts. The first model, which is just describes the kinetic energy of electrons propagating in the system. Second part is superconductivity. It's simply S-wave superconductivity. And then the third part is an interacting term, which I'm going to give you the details of it. So how does the kinetic term look like? So the kinetic term is defined by this Hamiltonian, but it's probably better just to sketch it out. So it's a Hamiltonian, which is a ladder. Okay. It has in these blue hoppings and in the green hoppings just spin-independent hopping. So this is another model for spinful fermions, just electrons. And then in these red bonds, there is a spin-orbit coupling, but only spin-orbit coupling. Okay, so this is a peculiar limit of the Kreutz ladder, which has the following neat characteristics. So if we look at the low energy excitations in this system, so if you do an envelope function approximation for the kinetic Hamiltonian, you can cast it in the following form. Here, P is what the momentum, Sz is the spin Z component, and this zeta is a Pauli matrix which indexes left and right. Okay, and this has the important consequence that in this model for low energy excitations, the two edges decouple. Okay, so moreover, you can locally do something with one of the edges without influencing the other edge. Okay, so if you apply some term which gaps out one of the edges, the other will remain untouched by this term. Okay, so this is a really nice property of this model that you can address the two sides separately. So for instance, if you gap out this term with an external magnetic field, then you still have Dirac-like fermions on the other edge. Okay.
László?
Yes.
Before I get completely lost, so the two sides are representing the Kreutz ladder representing the two possible spin states.
No.
No.
So each white dot is a spinful electron.
Okay.
So there are
but each side.
Each side has spin up and spin down. Okay. Each side has spin up and spin down. So if these two sides encode a fourfold degenerate ground state, fourfold degenerate state, a fourfold. So these two sides together have to be represented by a four-dimensional Hilbert space, because we have spin up, spin down, left, spin up, spin down, right, and that's why. So here, so this Sz, zeta z is a four-dimensional matrix. Okay.
Yes.
Good. So apart from that, then we have superconductivity, or we add proximity-induced superconductivity in our system, which is just like a typical S-wave superconductivity. So this is not very fancy. It is what you expect in most cases when you add a superconductor next to your system. And then we have this interacting term, which is not Hubbard, but it's local. I am going to give you a slightly more intuitive picture how this looks in 2 slides. Okay, but it is something where two spins on neighboring sides flip at the same time. Okay, and this is a Hamiltonian which was inspired by one of the bosonized papers. I'm also going to give you a bit more detail on that if you like, but this is again something which is not overly complicated, certainly not something which is 3-body and further interaction. Okay.
So this interaction is just local for each edge, right?
So this interaction, yes, in principle, in our case, but you could put this interaction also across the ladder. But so what we really want to do is somehow get rid of one of the edges and then focus on physics on one of the edges, because that is representing for us the edge states of a topological instrument. Okay. Yes. Good. So this is a nice model because we can treat one of the edges separately. It has explicit superconductivity and interactions, and it also has time reversal symmetry. So one of the key requirements in these bosonized pictures was that you addressed systems where you have time reversal symmetry. It was also I forgot to mention at that point. Okay. Good. So just to convince you that indeed you can gap out independently the two edges, this is the spectrum, the non-interacting spectrum when I add magnetic field on the left. So this is the spectrum where I colored it according to left and right. So if I add a magnetic field on the left, then my red states become gapped, but the blue states who are localized on the right remain ungapped. And you can also verify that this signature of the Hamiltonian, that spin up and spin down go in the opposite direction in the two edges, can also be seen here in these things. So on the right, which are the gapless states, I have spin up propagating in the left direction, up direction, and spin down propagates in the other direction. And if you go to the other side, then the colors reverse. Good. So as topological insulator edges were one of the first suggestions to look for Majorana fermions, it would be also useful to see Majorana fermions in these systems. So it is also another confirmation that this is a useful model. And indeed, this is what we find. So if you make a finite size system where you gap out most part of the system by a superconductor, and parts of this one leg with a magnetic field. This is the Bogolyub-Bogosian spectrum. There is the two zero modes which represent Majorana fermions, and then the wave functions also show that you have localization on these interfaces. Okay, so this again confirms that you can localize the zero energy excitations on the interfaces, which is only defined on one of the edges. Okay. So and then this is in parallel with the Fu and Kane's proposal for Majoranas in topological insulators. Good. So now let us go to the analysis of the interacting system. Okay. So now this is entanglement entropy, which is a useful quantity to look for phase transitions in general for DMRG calculations, because if you have highly entangled states where you somehow the states occupy all the system, then at critical points, then this entanglement entropy tends to diverge. So when you tune the parameters of your model, it can capture phase transitions. Okay, so this is the model what we considered here. A finite but relatively long ladder. It was, I think, the active part here was 100 sides long, and then there were some additional 20 and 20 sides buffer on the two edges. So the red region was superconducting, and in the blue region we considered this interaction. We also played with the chemical potential, and additionally we also added here an additional superconducting pair potential. Okay, so here in this picture we fix, so there is no delta prime. We only play with the interaction strength and the chemical potential in the interacting region. So what we find that in this point where there is no interaction and there is no chemical potential, we just would have a Dirac fermion. Okay, a single Dirac fermion, because the other edge is gapped by the superconductor in the red region. Okay. And as we play with the chemical potential, the system still remains metallic, as you would expect. Like if you are doping the edge of the topological insulator. Okay, but if you play with a pair potential, then it becomes insulating, and then you can also see that the entanglement entropy also drops. Okay, so then this means that you somehow we can understand this weakly interacting part. Okay, but then as you push interactions to stronger and stronger values, you see that there is marked phase transition happening somewhere around 1.5, and then there is a pretty large region in phase space which sort of behaves monotonically. Okay. And then as you increase interactions further, there is another phase transition which is captured in this region. Okay. So this is nice because interactions did something non-trivial in this system. Okay, but now we want to characterize further what happens with this system as we tune interactions. So I'm going to show you the excitation spectrum of this system. So the excitation spectrum is a so with DMRG we have access to the full many-body spectrum, the certain parts of the full many-body spectrum, the lower lying energy eigenstates. So both the eigenstates and the energies. So we can do really a lot of information from them. And this is what we find. So now again we set the chemical potential and the delta prime to 0, and we only play with the interaction strength. So in the whole Hamiltonian there is a single quantity which is invariant, which is the parity of the wave function. So we can do a DMRG calculation in the globally even and in the globally odd sector. Okay, so that's why we have I denoted here the 4 lowest lying states by even 1, even 2, and odd 1 and odd 2. So these are these colorful points here. And then there is the rest of the spectrum, which we could also label with the appropriate parity, but it is not that important. Okay. What is important is, as you see, that as we tune the interaction strength, at some point here, so this is now a slightly smaller system than what we calculated in the phase diagram, but there is a region where 2 even and 2 odd lowest lying energy eigenstates share the same energy. Okay, so this is the excitation spectrum. So I always subtract the lowest energy from everything, but nevertheless you can see that here the 4 lowest level states coincide. Okay, and on top of that there is a markedly large gap which is throughout this region stays there. Okay. So there now we are collecting the checkpoints for parafermions. So first checkpoint was that there is a novel phase as I include increase interactions. Second checkpoint is that we have a 4-4 degenerate ground state. Okay, so so this is promising, but we still need to do some further work. Yes.
So, then before okay, so because you were talking about excitations, but now actually one of those is the ground state.
Yes, yes.
Okay.
Yeah.
Okay.
Yeah. So this is a yeah. So the ground state here.
E1 is the ground state.
Yeah. Yes. E1 is the ground state. Yeah. And so this is not a zero energy excitation throughout the system, but this is indeed the ground state. And here I have several states which have at zero energy. Okay, and so in this region I don't have zero energy excitations. In this region I do. Yeah. This is important. Yes. Good. Okay, so let's look at some local quantities which in some sense characterize robustness of these wave functions. So the very first local quantity, well, robustness and localization of the wave functions. The very first quantity which we calculated, and I'm not giving you the numbers because it's really encoded into this single line, is that if we now so now from now on we are going to focus on this this part of the spectrum. Okay, so the 4-4 degenerate ground state, and because this part we understand as a essentially a non-interacting regime. This is a very strongly interacting regime, but here is the place where something interesting happens, which is this 4-4 degeneracy. Okay, so if you add any local charge fluctuation to the system, which is represented by this charge by this density operator, so this n is a density operator localized at any side of the system, then if you calculate the matrix elements of the 4 ground states with any local charge operator, they are going to be proportional to the unit matrix, which means that that charge fluctuations are unable to do anything with the ground state. Okay, so this means that the charge fluctuations will so the ground state degeneracy is robust against charge fluctuations. Okay. So what about spin fluctuations? So in this system, if we calculate the expectation value for the SY direction, then we find that, so this is now, I'm showing the expectation values in the even sector. The odd sector shows the same picture. So what you can see here is that these are these very, very small dots from your perspective at individual sites. And then the size and the shape and the color of these bigger circles represent the expectation value. Okay, so this means that one of the states has a strong polarization in the negative y direction. The other state has a strong polarization in the positive y direction. Any other spin components remain zero. Okay. This is also true for both in the even and the odd sector. So this means that if you add a magnetic field in the y direction, the system is going to respond to it. So, but this is not not a big problem from the perspective of us, because we wanted to have a system where time reverse asymmetry remains. Okay, but nevertheless, this confirms that the time if we break time reverse asymmetry, then the system is going to lose this protected property. And now, just to highlight, and so why SY? Okay, you might ask. And if you rewrite this interaction term into the language of spins, then it becomes immediately clear why SY. Because this interaction is actually, in the language of spins, something very simple. It is an anisotropic exchange. Okay. So, and in this this perspective, it's an anisotropic exchange. So it does not favor x direction, but it favors the y direction, and the z direction is here with a zero amplitude. So it's absolutely favoring the y direction. Okay, and indeed, if we would tune the interaction strength in the negative, then this reverses, and then we would have a spin polarization in the x direction. Okay. And so this is important because anisotropic exchanges can be engineered in certain systems. So there are these new novel van der Waals materials where magnetism, so magnetic van der Waals materials where magnetism is linked to strong anisotropic spin interactions. So this might so we can sort of find systems where which would generate this type of things, this type of interactions. And the third thing for local quantities is that we can also calculate the expectation value between an even and odd state of a single creation operator, a single annihilation operator. Okay. So this asks us, where can I put a single charge excitation into this zero energy ground state? Okay, and it puts it onto the interface. Okay, so I have interface localized states which are robust against charge fluctuations. Okay, good. So the third characteristic bullet point which I still need to address is whether these excitations are time reversal invariant Majorana fermions or indeed parafermions. And the big difference between time reversal invariant Majoranas and parafermions is their Josephson signal. Namely, if I calculate somehow, if I introduce an interface where on one side I have superconductivity, and on the other side I have a superconductivity and additional phase bias. And as I tune the phase bias, I need to follow how my ground state evolves. Okay, and in this setting, So this system allows us to really track what happens with states localized at these interfaces and calculate the Josephson spectrum and isolate the Josephson current going through essentially two of these zero energy excitations. Okay, two of these modes which are localized to the edge. So what happens here is so I plot now this is a configuration where I made a not very long junction. So if I would make a junction which is very long here, that would mean that these excitations are very exponentially localized to this interface. And if I make this junction very long, then I cannot pass a current through here because there is no overlap between the my zero energy modes. So I have to add a small hybridization. Okay, and in these calculations, this was like 8 sides long. So 8 sides long, which meant that so just to remind you, I had here. So I'm roughly at this point. At this point, my I have a gap in the excitation spectrum which is on the order of 0.5. Okay, and if I go to these setting where I have 8 sides here, then the splitting of the zero mode is 10 to the minus 3. Okay, so it's very small. Nevertheless, it is accessible from these calculations. Okay, and then what I can say here is that I can calculate as I verify. I can calculate the spectrum as I verify, and then you can identify a couple of crossings between these bands. And then you can also verify that these crossings are proper crossings and there is no hybridization. Okay. So if you look at the literature, especially in the bosonized language, there are a couple of crossings which they attribute to time reversal symmetry. So which are, for example, when phi is equal to 0 and phi is equal to pi, then the system recovers proper time reversal symmetry. Because if I introduce a small phi, then that breaks slightly time reversal symmetry. But at 0 phi, especially in the even in the odd sector, I have to have a degeneracy. This is the fingerprint of Kramer's degeneracy in the odd sector. At phi equals pi, these crossings are also protected by Kramer's degeneracy. But then there is also an additional thing happening here, which I'm going to slightly address in the next slide. But nevertheless, so these points are protected by time reversal symmetry and the parity anomaly, which I'm going to just slightly address it again. And then there is also this crossings, which you can see here. So you can also track them back. The fact that these are not splitted up to the local parity of these states. Okay. So what happens here if you start at this blue state and you very slowly the phase bias? So you slowly follow the blue line. You cross the crossings and you remain on the blue line. And then when you arrive at phi equals 2 pi, then you continuously evolve to the orange line. Okay, and then you can follow yourself through. So from the orange, you are continuously evolving to the green. From the green, you are continuously evolving to the red, and then red gives you back to blue. So you had to go through all the 4 states as you tune phi. So you have an 8 pi Josephson junction. Okay, but then so there is this issue. So when I was reading the bosonization literature, it was always puzzling me because they said that the parity of the junction. What do you mean by the parity of the junction? So I have a big system. The global parity is a good quantum number, and the local parity is something which is not a good quantum number. Okay. So this bugged me, and especially because this requires this has to do with the preservation of these crossings. Okay. And this system is nice because it lets you address these type of questions separately from a lattice, on a fixed lattice model. So what happens here? So if you do a calculation which has this type of setting, so you have here a region which has the phase bias, and then you calculate the whole spectrum, excitation spectrum, then if you focus on the low energy story, you get back this same picture, but there is an extra state plunging towards zero as you cross phi. Okay, so this is alarming. Okay, but thankfully this extra state lives on this side of the system. Okay, so you can find the localization properties because you have the wave function in your hand. You can analyze all the properties of the state, but it lives on this side of the system. Okay, because you have not just one Josephson junction here, but two. Okay, you have a Josephson junction from here to here, but there is also a Josephson junction from here to here. Okay, so but nevertheless, so in this setting, here something happens which is not continuous, and so here there is this one gray point here which is sort of heralding that there is something wrong. So here, really, in this geometry, you cannot have this nice continuously following lines here. Okay, because here something more states enter the game. Okay, so in order to have these nice continuous evaluation, we have to do something with these states. Ideally, it would be nice if you could pin them to zero. Okay, so you can pin them to zero. So what we do is that we introduce a field where we have a magnetic field, which we have seen that they pin Majoranas. Majoranas will remain at zero. And if I increase this region where I have a magnetic field, then the Majoranas remain really localized at zero. So they are not going to be moving across the spectrum. And indeed, this is what we find, that now we have got rid of these states which plunge to zero, and because they remain all the times at zero. The thing what we pay here is that now instead of having a 4-fold degenerate ground state, we are going to have an 8-fold degenerate ground state because we have to account for the Majoranas as well. Okay, there is another thing which I have to tell you here is that first when we calculated the DMRG wave functions and we looked at the Josephson spectrum, we got these orange points. Okay. And this was really puzzling because it is not an 8 pi, it's a 4 pi. Okay, we got these orange points, but we got also these weird outliers. So then we sat down and we told Botond, the PhD student, crank up the parameters of the DMRG calculation just to make them a bit better. So if they are really just Majoranas, then these outliers should shrink back. And so when he was cranking them up, it did not shrink back, but it basically filled out this thing like homogeneously. So it was like you add more and more precision, and then you seem to lose it in the results. And then what indeed saved us was we took states, which was basically these orange states, and then we did a reorthogonalization of the Hamiltonian with these states, and then they gave back these nice smooth curves which are here. Okay, so this is like a DMRG plus a reorthogonalization of the ground state, which gives us the proper ground state description of our system. The nice thing here is that we can also focus on the Majorana part, so which is just confirming that if in the Majorana part we do the reorthogonalization, so which means that we increase the system size here, we decrease it here. Then in the Majorana part we have a typical 4 pi behavior. So in this system we have like a 2 pi junction, which is basically this thing, which you can see here. So this is the proper energy spectrum. and this is the excitation spectrum, and this is the excitation spectrum focusing on the very low energies. So we can have a 2 pi, 2 pi, 4 pi, 8 pi in the same system, and we can focus on the different Josephson junctions here. Okay, I think I will skip these and basically go further. So what we find here is that I have shown you that we have a four-fold degenerate ground state, which is robust against charge disorder, or zero energy excitations live on the interfaces. And indeed, we find that with these interactions, we can make a 4 pi Josephson effect. That means that we have indeed managed to come up with a system where we have these parafermionic excitations. So why is this nice? I mean, this is nice because it gives us a condensed matter setting where it gives us a model setting where we can model these type of systems. But it also made us to realize that you don't really need the edge of a topological insulator here, because the lattice model itself is sort of a recipe where we can find parafermions. And indeed, so the lattice model points towards the realization of these phases in systems which are built out of, in some sense, quantum dots. Okay, so of course, one of quantum dots or maybe codatons, but in particular, so there has been in the recent couple of years a real progress towards fabricating quantum dots in a setting which would be really beneficial for the realization of our systems. So there have been some. So there are two Nature papers which focus on. So first of all, there is a paper by Hendricks and co-authors where they have managed to make. Right, this is not yet a ladder, but it's already 4 sides. But the extension of this work is now here. They have managed to make 8 sides. So this in a setting where they can tune normal hopping, interactions, and spin orbit coupling roughly on the same energy scale. Okay, this is an important thing. And there was also from Delft recent papers, recent progress where they had also the inclusion of superconductivity in the system. So they have some really nice control over these parameters, what we would need to fabricate these ladders where we might find parafermionic excitations. And so with that, I think I would like to finish my presentation. So in the beginning of the week, our work appeared on arXiv, and I would really like to have your opinion about it, and or if you have some suggestions, I'm really happy to talk about. Okay, thank you.
Questions?
Yep.
So I didn't understand what you said about orthogonalization. Right? So
Yeah,
you find ground states, and they are energy eigenstates, and then they are orthogonal.
No, so this is an important point. So what happens is that DMRG is a variational method. Mm-hmm. So it gives you a ground state wave functions which are a given quality. Okay, and we also characterize this quality by the variance parameter. So the variance of the wave function is the difference of the expectation value of the Hamilton squared minus the energy squared. So and they were the variance was 10 to the minus 3. This means that when we are looking at the Josephson spectrum, we need the energy to be on the range of 10 to the minus 3, not the variance. So the variance tells you that even though compared to the 0.5 is really good, but compared to the 0 to 10 to the minus 3, they are not really good. So what we did, we took those not really good eigenstates And then we calculated the matrix elements with them of the Hamiltonian and the overlap matrix. So we had to solve a generalized eigenvalue problem. And those gave us really, really good quality eigenstates.
Okay, so I mean, you find the ground state, but then you had 4 states. So the higher lying states
We also included. Yeah.
And I mean, you find them by saying I want to minimize the energy and being orthogonal.
Yes. So this is again, and this is a particular thing of what type of DMRG software you use. So we used there is a code developed in Budapest, but for that particular part we used iTensor. And iTensor you always have to look for a single state one at a time.
Yeah.
And sometimes this is like an important but technical detail that you have to be very careful of the quality, especially if you are looking at these very highly degenerate states.
And then you say, I'm only interested in subspace. I project my Hamiltonian on that subspace and diagonalize it.
Yes. Yeah.
I have a second question. I don't see any raised. That was about you gave us had this checklist about parafermions, and then, as I understand, it's the fact that it's actually written here in the summary. So is this a strict implication? Whenever you have this 8 pi Josephson one, you have parafermions. Does this imply that the operators satisfy these commutation relations?
So this is a good point. I mean, this is discussed to a certain degree by Alicea, whether what would be the really good name of things which people call parafermions in some papers which have 8 pi signal. So sort of right now, still people call these parafermions. Really the proof of the pudding would be to whether you could do if you would braid these things, whether you could realize things which you would be able to realize with parafermions. And as far as I understand, so far, I mean, no one did braiding with any kind of lattice model, but you could still make the predictions to a certain degree with polarization. Although there is also some technicalities which I am not very familiar with. But as far as I understand, these would also be having the same type of algebraic structure. Yes?
Maybe because I don't know anything about DMRG, but because your model, you have a model like a toy model for the 2 edge modes of the TI. So, but then you put the interaction into that toy model.
Yes.
So it, like for me, the size in that toy model is very different from the lattice size of the realistic model, realistic system. So how can you justify this?
So that's a good point, but in the end, so you mean the size of the interaction?
Yeah.
So in the end, this is an important point, because when people looked at, so originally everything, the inspiration comes from the edge of the TI. But in the end, when you realize that this is a lattice model, in the end, we really say that the way how we realize this, our model, we should go to a system or a platform which is more realizing lattice models. So in the quantum dot setting, where you have a lot more control of the local parameters, a lot more obvious what really happens. And so it's really not a model for a realistic TI, but it was just inspired. So the only thing what we take from the TI is that we have to have sort of helical electrons somewhere. Okay. Thank you for the question.
But then, maybe I missed this point in the expression. In the context of quantum dots, how do you recover the physics of it with the TI?
Well, so in the context of quantum dots, if you set the kinetic term that it confirms the Kreuzladder,
okay,
then then you recover chiral electrons moving at one of independently from each other on the two legs of the ladder. So the Kreutz model, I mean, this particular limit of the Kreutz model tells you if you make quantum dots like this, and there is no interaction at this point, okay, then you are going to have chiral states going, spin up going up on the left and down, spin down going down on the left, and they are not talking to the right. Okay, that's the point. And then you can gap out one of the ranks with maybe a Zeeman term, and then you can have in a quantum dot array an isolated helical Dirac system.
Okay, this is clear, but that means that I go to the lab and I need to be able to build up this set of dots that have this specific property.
Yes.
Because in general, if I make an array of dots, I will have all the possible type of spin dependent.
So this is true, and this was also the point of these recent experiments, that they have they have a lot of gates where they can in principle tune all these parameters sort of independently. So spin orbit coupling, proper hopping, and interactions have their own levers through these backgates. Okay. And then, of course, you can also think about cold atoms, which is the usual way of when people don't know how to realize their own lattice models, then we say cold atoms. But I think so. Since I come from transport, I like this realization a bit more.
Yeah, I think that in cold atoms probably have at least on the theory more possibility to decide which type of hopping process you have or not.
Yeah, and maybe also the type of interactions. What you need is also a bit more tunable there. Okay. Thank you for the questions.
Thank you. More questions? And let us thank the speaker. Okay.
So you saw my email?
Yes, thank you very much. Thank you for your comments. Very good.